Hello everyone. This week we're going to go through the topic of circle theorems. So some of you have not been in school during the lockdown at all and have missed some of the lessons regarding circle theorems. So I'm going to make a whole load of a couple of videos going through all the circle theorems. And for those of you that have been going to school and kind of attending the lessons, it's an opportunity for you to go back over the content and see what you've understood. So, going back over things is really going to help you remember all the different facts about circle theorems. And then we're going to go over some extra problems as well, so you can kind of get an idea of what type of questions you're going to get in an exam. So this week is going to be broken down into the following. So this lesson, I'm going to go through every single circle theorem. I'm going to demonstrate it on a piece of software as well. And then I'm going to go through some examples that some of you have emailed. So some of you have emailed me questions that you didn't quite know how to do. And so I'm going to go through those. And that's lesson number 1. There's going to be 2 videos for you to watch. Okay, lesson number 2 this week. There's going to be some questions for you to have a go at. Lesson number 3 is going to be some exam questions again, and then that's the one you've got to submit. So you've got to make sure you submit lesson number 3. So make sure you have a go at those exam questions. So the video will go through exam problems. It's going to be one of those, you watch and pause and have a go at something and then see if you get it right. And then lesson number 4, you'll be in school. But for those people that are at home, I'll post something else for you to have a go at some point during the week. Okay. Now, by the way, so this video we're going to go through each circle theorem, and then we'll look at some example questions. In the second video, we'll look at some example questions from Caboodle. And by the way, you can always download these kind of like pictures online. So this is just a Google image of all the different circle theorems, and they're very, very useful. And it might be worth you having a download or making something as colourful as this for you to remember. Okay, so let's not waste any time. Let's go through all the circle theorems. Okay, so first of all, this is more of a fact, really, rather than a theorem. Actually, I really shouldn't muddle my words, but this is not one of the official circle theorems. This is more of like something you should really know, okay, in general. But if you have a circle and you draw 2 radii, so remember what radii mean. Radii means like more than one radius line, so it's the plural. But if you draw 2 radius lines or radii, they will always make an isosceles triangle. So for example here, this is a radius line and this is a radius line. So the triangle formed by those 2 lines is always going to be isosceles. And if you think about it in a logical way, these 2 lengths are the same. And we know in an isosceles triangle, 2 sides of the same length, it makes an isosceles triangle. So because the radius of the circle doesn't change, if you draw 2 radius lines, it's always going to make an isosceles triangle. And then these 2 angles up here would be the same. And same on this one down here. I mean, these 2 lengths would be the same. And then these 2 angles in the corners would be the same for that triangle there. Okay, so that's kind of like the first thing to remember. Now, literally all the circle theorems that you do are based on this one fact. Okay, so they all kind of stem from this one rule, because you can just kind of modify and use it to prove other things. But all the circle theorems kind of come from this one rule. And then when you look at proof, when you look at some algebraic proof of why these circle theorems work, we always use this at some particular point. Okay, now, circle theorem number 1. Now, this is the first proper one, and it's difficult to see, but I'm going to demonstrate it in a minute. So, first of all, if you have 2 positions here, let me actually get a highlighter. If you have 2 positions like this, which are kind of fixed, okay, on the circumference, and then if you pick a third position, let's do it this way. If you then draw that from those 2 fixed positions, if you draw 2 radius lines and to those fixed positions, okay, and then you have a third point on the circumference. So on the circumference, anywhere between those 2, so anywhere on this green line. So this is kind of like the major arc. So here's these 2 blue points are fixed, and the radiuses are joining them up. Okay, if you pick a point anywhere on the circumference, like I've done here, so here's a point I've picked, and you join it to those 2 positions. Okay, the center angle on this side of the shape is always twice the one on the circumference. And this is the definition you need to know. Okay, so the angle on the circumference, sorry, the angle at the center. So the angle at the center is always twice the angle of the circumference, and this is kind of like circle theorem number one. Now later on you'll be proving this with algebra as to why that angle there is double the one at the circumference. But I just want to demonstrate this to you on a piece of software, because down here you might have read this already, but it says look for an arrowhead shape, but that's not always the case. And I want to just demonstrate that here. So for example, this is a piece of software that I use to demonstrate these circle theorems. And I mean, you might not be able to clearly see this, but here's that arrowhead shape. And you're going to have to ignore the decimals because the software isn't great with the decimals in terms of rounding them correctly. But if you look at the number part, the integer part, it says it's 60 there and 120 there. But remember I said to you, if these two positions, okay, are fixed, then this third point on the circumference can be anywhere on that major arc between those two. So if I literally move it here, you can see that double 60 is still 120. That angle, if you double it, you always get the one in the center, and that third position can be literally anywhere like this. And if you double it, you get the one at the center. So that top angle that top point on the circumference can be literally anywhere. But last week your teachers might have said look for an arrowhead shape, but that's not always the case, because you could have something like this, which is more of like a diamond shape. So for example, if you double 124, you get 248. So you can see that the theorem still works as long as that third position is between those two fixed positions. And remember, the angle that you get is the one on the opposite side of the shape. Okay, that's another thing, because sometimes students think it's the one on the inside, but no, it's the one on the outside. So if you double the one on the circumference, you get the one on the outside. So it's a bit crazy because this theorem works no matter what it looks like. But these two positions kind of stay where they are, and that third position is allowed to be literally anywhere you want it to be. And you double the one on the circumference and you get the one at the center on the outside. Okay, circle theorem number 2 is really just an extension of circle theorem number 1, really. Okay, but if you have the following, if you have a chord, okay, now remember what a chord is. A chord is a line that goes through the circle from circumference to circumference, but it doesn't go through the center, because then it'll be a diameter. Okay, so if you have a chord, so here are the two ends of the chord, okay, and you don't really need the chord, you don't actually need to draw the chord, but it's just easy to visualize it, to see what it is. But if you have a chord like this, and these are the two end positions on the circumference, if you make an angle with any point, okay, by the way, let me highlight this. So you've got this, remember when you draw a chord, it chops it into something called segments. Segments being like the two halves that you get when you chop it like this. But if you pick a point in the same segment, so anywhere in this green arc, if you pick a point on the circumference like this one here, and if you join it to the ends of that chord, okay, like so, and if you pick a second point anywhere on that green arc and join it to the ends of that chord, the same chord, then those two angles on the circumference will always be the same. They will always be the same. And later on you'll prove this with a tiny bit of algebra as to why that is, but you can easily prove it to yourself. But those two angles will always be the same, as long as those 2 points on the circumference are in that same segment. Okay, so they have to be in that same segment, and this is the rule that you need to know. So angles on the circumference in the same segment are equal. And I just want to demonstrate that with you here. So on this piece of software, and I hope you can see this clearly, but the red line is the chord. That doesn't change, okay? And you can see that these two angles, where the points are on the circumference, are made from that chord, and they're in the same segment. So for example, when I say same segment, like for example, you can't do it down here and a wall up there. It doesn't quite work if one's up there and one's down there. It doesn't quite work that way. But can you see that red line? And then these two points are on the same side of the circle, the same segment, and they're on the circumference, and that's important. Now, if I move these around, you can see that the angle does not change. They're both 32.46. They do not change, and it literally doesn't matter. I mean, I can swap them over. I can put it there. I can put this one down here. As long as they come from the same chord, that same dotted that same red line. And by the way, you don't even need to draw that red line in. So that red line, you don't actually need to have it drawn there. As long as they come from like that point and that point, they will always be the same. And as long as they're in the same segment and on the circumference, they will always be the same. So if I change the chord, you can see that the angles change, but they stay the same size. They're just, sorry, they're the same angle, but the size is different. So if I change the chord, they both turn to 43.2, and I can move this one here, and they both turn to 17.47. If I move it here, they're both 75.26. They're both the same angle, and it doesn't matter how much you change it. Okay, and by the way, guys, I'm going to put a link to these files so that you can play around with them, so you can sort of see it for yourself, but you can see that they do not change. Okay, that is circle theorem number 2. Angles on the circumference in the same segment are equal. And by the way, this is a fancy definition of it. I don't tend to use that one because the word subtended means that they kind of are fixed from this location here. Okay, let's crack on with the other ones. Okay, this is circle theorem number 3, and it's to do with cyclic quadrilaterals. Now, first of all, you need to understand what it means by cyclic quadrilateral. First of all, quadrilaterals are any four-sided shape. But the word cyclic means is that the corners of the quadrilateral are on the circumference of a circle. Okay, so that's what it means by cyclic quadrilateral. It means it's a four-sided shape where all the four corners are on the circumference of a circle. Now, the really cool thing about cyclic quadrilaterals is that the opposite angles always add up to 180. Okay, so this is the rule that you need to remember. This is the rule. Opposite angles in a cyclic quadrilateral add up to 180. Now, by the way, I'm going to reiterate that one key point. It has to be a cyclic quadrilateral, and a cyclic quadrilateral has all four corners on the circumference, and that's the most important thing. And then the opposite angles are the same. Now, by the way, when I say opposite angles, it includes these two here. So these two orange ones would add up to 180. So, for example, if this was 100, then the opposite one would have to be 80, and that's as simple as that, really. So that's what it means by that. So opposite angles in a cyclic quadrilateral add up to 180. Now I'm going to demonstrate that. Okay, so here's a cyclic quadrilateral, and I've got the computer to measure the angle in this corner and measure the angle in this corner, and then I've got the computer to add them together and tell me what the answer is, and it's telling me that they're currently 180. So these two angles here, even though they're different sizes, they add up to 180. Now, this cyclic quadrilateral, notice that all the four corners are on the circumference of that circle. No matter how much I move it, look at the total there. I mean, by the way, there's a link to this, so you just find that link and it will take you to this page. But you can see that they add up to 180. It doesn't matter where I move those 2 points. So I can make something ridiculous like this. This is a Scylla quadrilateral. It's got four sides, but that's 150.5, and that one's 29.5. And guess what they add up to? That's right, they add up to 180. And I can put that point up there. I can move this one around there, and I can put that really close to that one, and they still add up to 180. Now, by the way, it's hard to visualize it on this one, but it's a cyclic quadrilateral. But this large angle is opposite that large angle, and this angle is opposite that angle, and those are the two that add up to 180. And it doesn't matter if one of them is obtuse and the other one's acute. Well, the other one would have to be acute if the other one's obtuse, but they have to add up to 180. And remember, all four of them would obviously add up to 360 because it's quadrilateral. But here you can see, again, they add up to 180, and it doesn't matter. And also, the radius of the circle has no effect on it either. So I can make the radius bigger and they still add up to 180, or I can make it really small and they still add up to 180. They will always add up to 180, the opposite angles in a cyclic quadrilateral. But remember, all 4 points need to be on the circumference for it to be cyclic. Okay, right, circle theorem number 4. Okay, easiest one of all, and it's really an extension of circle theorem number 1 again. But if you draw a diameter line, okay, this is a diameter. Remember, a diameter is a line that goes through the circle but through the center, and that's a diameter. It's a straight line, okay. And then if you pick, and remember, when you draw a diameter, it chops it into a semicircle. So here's a semicircle. So semicircle is half a circle. But if you pick a point on the circumference in that semicircle and then join it to that diameter line, so here's a point on the circumference. If I join it to that diameter, then that angle on the circumference is always 90 degrees. Okay, so this is the definition you need to remember. Angle on the circumference in a semicircle is always 90 degrees. And really, it's an extension of circle theorem number 1, because if you look at this angle here, well, okay, how much is the angle on a straight line? It's 180. And if you half it, you get 90. So that's why that one's 90. But then this would have to be a diameter line. Okay, that's the important. This is a diameter. And then you have to pick a point on the circumference and join it to the end of that diameter. And then that angle would be 90. But it works on the other side as well. So here's the diameter. Okay, and then here's a point on the circumference. And then here's the triangle made with the diameter and that point on the circumference, and that angle is always 90. I'm going to demonstrate it as well. Okay, so here it is in action. The great thing about this software is that when it finds a right angle, it automatically puts a square in to say it's a right angle. So I'm not telling the computer to draw a right angle. It's doing it because it is a right angle. But you can see here's a diameter line. Okay, and there's the third point, and you can see no matter how much I move it, as long as it's on the circumference, it will always make a right angle. And I can change the diameter like this, and it stays as a right angle. It's really, really cool. And I can put it like that, and it's still a right angle. And I can put that right like this, and then it's still a right angle no matter how much I change it. As long as that's a diameter, and that third point is on the circumference, it will always be a right angle. Okay, rule number... Okay, this is wrong, sorry. Okay, sorry, that was circle theorem number 4, by the way. Okay, circle theorem number 5. Okay, now this is just another thing that you need to remember. Okay, so first of all, tangents. This is circle theorem 5 to do with tangents. Okay, remember, a tangent is any line that touches a circle in one location. So, for example, it's the line, it doesn't go through the circle, and it doesn't miss the circle, but it touches it in one location. So here, for example, this tangent line comes across, it touches this point here, and then carries on like this. Okay, now one thing, okay, two things to remember, sorry. Okay, if you have a tangent and then a radius line, the tangent and the radius always meet at right angles. So here's a radius line, and here's a tangent touching the circle where that radius meets. Then that will have to be a right angle. So a radius and a tangent always meet at 90 degrees or right angles. Okay. Now, the cool thing about tangents is this: if you draw two tangents like this, so here's the blue tangent, and you draw another tangent in such a way that it meets the other tangent, okay, then these two lengths are the same. Now the length, is from here. Okay, let me actually get a better colored pen. Let me get a red colored pen. So from here, okay, let me do it properly. Okay, so from here to here, so where that circle, where that tangent meets the circle, and then from here to here, so from here to here, and from here to here, those two lines would be the same length. So you put a dash on them to tell them that they're the same length. Okay, and so from that position to that position where the tangents meet, from that position where it meets the circle to where the tangents meet, will always be the same length. And together with these two radii, that's a right angle, and that's a right angle. This shape is always a kite. Okay, a kite is symmetrical. Okay, and obviously this length would be the same length as that length because they're the radius, but that will always be a kite. And remember, kites are symmetrical, so you can draw a line of symmetry like this through them. Okay, so two tangents will always make a kite if they meet each other, obviously, and that distance from there to there is always the same length as that distance from there to there. Where the tangent meets the circle and where the tangents meet each other, that length is always the same. Okay. Now, that's circle theorem number 5 in a nutshell. Okay, and I don't really want to demonstrate that because it's more of a fact, really, and we can use it to prove other things as well. We'll look at some questions in a minute. Okay, right. This is the hardest, no, not the hardest, but it's the trickiest one to remember. And this is the circle theorem number 6, and it's called the alternate segment theorem. And it works like this. If you have a tangent to the circle, so this is the tangent line. Remember, a tangent touches a circle in one location. And then if you pick, so this is the location where it meets the circle. Then if you pick any 2 points in the circle and make a triangle from that location where the tangent meets it. Okay, so this is a triangle. And remember, those 2 points have to be on the circumference, and the third point has to be on the circumference, and the tangent has to go through that point. Okay, then this angle here is exactly the same as this angle up here. Okay, and the reason why it's called the alternate segment theorem is because this chord here chops the circle into 2 segments, and the angle in one segment is the same as the angle in the other. Now, by the way, this angle is made from the tangent and the chord. Okay, so it does stick out the circle a little bit, but it works in both directions. So this angle here is the same as this angle here. Okay, and that's the hardest one to spot. But I mean, if you think about it, it's not really that difficult. If you have a triangle with all the 3 corners on the circumference, and the tangent goes through one of the corners, then the angle on one side between the chord and the tangent is the same as the one in the alternate segment in the corner. And that's literally kind of it. So if you know one, you can easily work out the other. Okay, so there are all the circle theorems, and you do need to know them and you need to practice them. In the next video, the one following this one, which I'd like you to watch, I go through some example questions where I use some of the circle theorems to have a go, and they're from Caboodle. Okay, and then the tasks, by the way, don't stop just yet. The task that I want you to do is this one. Okay, oops, let me minimize it. Okay, it's a code breaker. Okay, so you have to work out the missing angles, and then it will make a message, and then if you get the message right, which you should do, maybe you can email me or submit the message so I can see if you got it right. It'd be kind of cool if everyone gets the right message. I actually don't know what the message is, so you're gonna have to tell me what it is. But that's the task that I want you to do. There's 2 sides. I think there's 2 messages that I would like you to have a go at. But that's today's task. Okay, thank you for watching, guys, and maybe watch the next video as well.